We're going to start this with a thought experiment, a concept, and you may have seen this demonstrated by your physics teacher. So there's this little bit of apparatus here. It's rather pleasing. A little spring-loaded mechanism. You have two balls, ball bearings. A is just going to be dropped vertically, and B is going to be projected horizontally, constant velocity, but they're at the same height. So the question is, which ball will land first? Now, you may know this intuitively, or you may get stuck at this first point, because the counterintuitive incorrect answer is that B has more energy or more force or something, so it spends longer in the air, and that's just not true. So they both land at the same time, so maybe you knew that, or maybe you intuited it. And the reason why is because they both have a vertical acceleration of 9.81 meters per second squared. They are both falling freely due to gravity vertically. So they both cover that vertical distance in the same time. It just so happens that ball B is also moving horizontally with constant velocity, so it also moves forward as well, but it's falling vertically. So it's this combination of vertical motion and horizontal motion which gives us the actual path of ball B, which is known as a parabola or a parabolic path. So this is the fundamental idea of projectiles, the idea that the components of velocity, horizontal and vertical, are independent of each other. That's a really key idea. We've mentioned that previously in an earlier video, but that is fundamental to what we are doing today. So to introduce this and also to recap kinematics in one dimension, which is what we've done in previous videos, we're going to look at a worked example. So this is Beachy Head, near where I live, beautiful walk, really high cliff. Don't get too near the edge, and certainly don't drop anything or throw anything off it. This is very much a thought experiment. So we drop an object off this 150 meter high cliff. So got a few questions. How long will it take to reach the ground? Okay, well, that's just a one-dimensional problem. That's a straightforward problem. We can just use our Suvat kinematics equations. We know that U vertically is 0. We're trying to find, we know S is 150 meters. We know acceleration vertically is G, 9.81, and we're trying to find the time. Yeah. So importantly here, U is 0, so UT is 0, so that is removed from the formula. Rearrange to make T the subject. We get root 2S over A. Top tip, always rearrange before you substitute, a much better technique. So we put the numbers in and we get 5.53 seconds. That's a long time. So we've got all this time falling vertically. What would be its speed on impact? Again, that's a one-dimensional kinematics problem. We can solve this in a number of ways. I'm going to use V equals U plus AT. Vertically, again, U is 0. A and T, well, we know time. We know A, we can work out the velocity 54.2. Up to this point, we have done nothing new. This is just straightforward, one-dimensional kinematics problems. Right, part C. What about if we'd thrown it horizontally with a velocity of 6.5 meters per second? So now we have our parabolic path. So we have this horizontal motion and also this vertical motion as well, this acceleration. Now that sounds really difficult all of a sudden. However, if we know the time for that it fell vertically, that is exactly the same. So this is the first key concept that students really struggle with. The time is the same. Even though it's moving horizontally, it is still falling the same distance vertically. So we know the time it takes to travel on this parabolic path. Only now it's moving horizontally as well with a velocity of 6.5 meters per second. We would always ignore air resistance, and that's a reasonable assumption at low velocities. So this becomes a very straightforward calculation. It's just V equals S over T, constant velocity calculation. So S equals V times T. We've made S a subject. We know the velocity horizontally is 6.5. We know the time is the same as it was before, so we can calculate the horizontal distance, which is 35.9. So this is really important. So we can treat the horizontal and vertical components of velocity independently, separately. They're not connected to each other. Very, very important.